acid and a strong base.
Yeah, totes. Yeah, I mean, we could react these guys together, right?
Oh, yeah. Okay.
Is it okay if I erase this so that I can do some more examples? Yeah, we cool? All right, so I think it's a little bit easier to understand this stuff when you're talking about weak acids and weak bases or weak acids and a strong base, because then you have a situation where there's a little more back and forth between the acid in its solid form and in its ionic components. So what the heck am I talking about? Let's say we have this guy. Anybody know what that guy's name is?
Acetic acid?
Acetic acid, yeah, exactly, acetic acid. Anybody know where acetic acid is found? It's vinegar. Acetic acid is vinegar. Yeah, exactly, Kata. You got it. So acetic acid is a weak acid. How do I know that?
It's not the strong 6.
Yep, exactly. It's not one of the strong 6, so it's weak. So, looking at what we've got here, what is this guy in terms of our acid-base reaction?
That's the acid.
This is the acid. And this guy?
He's the base.
Uh-huh. And now when we're talking about this guy and this guy, this is where things get a little bit confusing, okay? Now, technically, water can act like an acid or a base, so it's difficult to know which part it's playing in the product side until you know which one this guy is, okay? So, this guy, the most important component here is acetate, and we'll talk about why when we do the Ti and Ni for this reaction. But the acetate is going to be your conjugate base, right? And if you know that this guy is the conjugate base, then what must this guy be? The conjugate acid.
I was like, how could water be an acid?
Ah, great question. Water can be a base when it does this, right? But it can also do this, right? Which would make it an acid.
You fancy.
So, how are we doing with this, guys? I'm gonna show you the Ti and Ni because I think it makes it a little bit easier to see why this guy is the conjugate base. This guy is just really hard to see. So if you can't see that, that's okay. But this guy is a little bit easier when you do the Ti and the Ni. Okay, if I erase and rewrite? Yeah? Cool. So, oops. Okay, so I don't have it written down anymore, but we looked at it before. These guys are all aqueous, right? So when we do our tie, they should all break down, right?
Yes.
I said last time that there was one exception to when you have an aqueous substance and it doesn't dissociate in your tie. Anybody remember what it was?
Steph. Same.
A weak acid.
Ugh.
Yeah. So weak acids are not going to dissociate. So we keep this guy together. Oops, frick, why do I keep doing that? Okay, and the reason being, again, is because it doesn't dissociate completely, we know that there's still a lot of this guy left in solution. Does that make sense? I'm sorry for you guys having to see my hands so up close and personal. It's really disconcerting to watch. But this guy is a strong base, will definitely break down, right? So we'll get sodium and hydroxide. Everybody still okay with me? I still don't understand when you add the word conjugate. We'll talk about it again, Alex. Sorry, I'm getting there. So on the product side, is this guy going to break down?
No.
Mm-mm. Solids, liquids, gases do not break down ever. So we got this guy stuck still. What about this guy? It's going to break. Why is it going to break? Why is this guy aqueous? Thinking solubility rules.
It's grouped with what's it called? Group 1 metal?
Group 1 metal, exactly, right? So sodium is a group 1 metal, which means that this guy is soluble, which means that we'll end up with an Na plus and an acetate ion, right? So do we have any spectators in this reaction?
Sodium.
Sodium. Does everybody see that?
Yes.
Sodium, sodium, right? So our Ni,
I have a stupid question.
go ahead.
Why did we leave together? We took out sodium, but we left carbon, hydrogen, and oxygen.
Ah, this is a polyatomic ion.
Of course it is. Okay.
Right? So we never break apart polyatomic ions and they're double Ds.
Got it.
Great question. Okay, so what we have left, oh my God, I don't know why I keep doing that. I'm sorry, you guys. Is these, right? So, this guy we said is our acid. This guy we said is our base. Everybody comfortable with why we said those?
Yeah.
Cool. So then the question was, which one of these guys is the conjugate acid and which one is the conjugate base, right? Whenever we have an acid-base reaction, we always end up with one product that's called the conjugate base and one that's called the conjugate acid, okay? That's just the way she goes. The reason being is, again, because of the nature of acid-base reactions, you always end up with an acid and a base, right? Meaning that one of them can always accept a proton and one of them can always donate a proton, right? Does this make sense? Conjugates, they're called conjugates because they come in partners. Does that make sense? You guys familiar with that word, conjugate? Like conjugal visits? Yeah, I know. It's terrible. It's on film now, forever. For the rest of my career. Cool. Puppy! So, when you look at something that has a minus sign on it, I think it makes it a little bit easier to see that this guy could definitely react with one of those, right? You picking up what I'm laying down?
Yeah, that's a nice little trick.
Yeah. So I think looking at the Ni makes it a little bit easier to see that this negatively charged ion can totally hook up with this positively charged proton, right? If it can accept a proton, that means it must be the conjugate base. Sorry. Meow. Alex, are you following a little better now? Or no? Cool. Awesome.
Do we only call them conjugates on the product side, or would that front acid also be conjugate?
So this is where things get kind of weird because it depends on, I know. Just to be the worst.
There's always like rules, but also exceptions to the rule.
Well, okay, so we call them conjugate acid pairs. Conjugate acid base pairs, okay? But only one of them is called the conjugate, okay? Generally speaking, the one that's on the reactant side by convention is called the base or the acid, and the one that's on the product side is called the conjugate whatever, acid or base, right?
Gotcha.
Now, that's by convention, okay? Now, here's what's going to freak you out, okay? Because there's nothing about... Why was the last conjugate? Why was the last example both conjugate in the products? So, conjugates, just like what Jessica was asking, conjugates by convention are always in the product, okay? That's just the way she goes. So we always start off with the acid and the base, and then we end up with a conjugate acid and a conjugate base, right? So, so here, if we know that this is the conjugate base, right, then what must this guy be? They always come in pairs.
I don't think both of the products are called conjugates, just one of them.
Conjugate acid.
Yeah. Oh, I just was in the chat.
Yeah. Because...
Oh, what?
Yeah. So, what we were saying in that first note bit when we were talking about the individual acid and its conjugate base, right? That was just looking at the acid and the base by themselves, right? Is everybody with me? Now we're looking at the acid and the base reacting together, right? And if we know that an acid and a base by themselves must also have a conjugate acid and a conjugate base, right? Then when they react together, they must produce a conjugate acid and a conjugate base. Does that make sense?
They all gotta hook up with each other.
Exactly. Exactly. Partners, conjugate. Does that make sense, Alex? Okay, let's do a couple more examples. I think it'll make more sense. Okay, so I'm going to do something that's going to really ruin your lives here, but hopefully will make things make a little bit more sense, maybe, kind of. I'm going to erase. Is everybody okay with me? The consistency in when to write it in the last few examples. So anytime we have an acid-base reaction, the acids and the bases are always the reactant, and the conjugates are the products by convention. Does that kind of help? The reactants are conjugates? In the first example? What? I don't think we had any conjugates in the first example. Am I crazy pants? We didn't have any conjugates in any of the reactants so far, did we? Only in products, I think. It's only in products, Alex. Sorry for the confusion. Right, but that was still product side, right? We had an acid on one side and we had the conjugate base.
Are they talking about when we dissociated from like HNO3 to H plus and NO, then we had that and the conjugate? Is that what they're talking about?
Maybe. Real solo acid or solo base. I think so, but I think generally speaking that hopefully the reactants being an acid and a base and the conjugates being a product, can that stick? Products or conjugates? Yes. By convention, okay? Now, okay, so this is what I wanted to get to in the next point, which is to say that why we call this one the acid and the base and this one the conjugates is totally a matter of convention, okay? If we are to flip this reaction around, meaning we put these as the reactants and these as the products, then these become the acid and base and these become the conjugates, okay? That's what I'm going to show you. So it's not about what the species are per se, it's about where they are in the reaction as it's written. Does that make sense? Okay, let me show you. So if I have right? I could easily have written the reaction this way. Now, this guy is the acid because it's donating a proton. This guy is the base because it's accepting the proton. This guy is the conjugate acid. And this guy is the conjugate base. So do you guys see what I mean in terms of it's just a convention? We're just basically saying acids and bases on the reactant side, conjugates on the product side, right? I could write these reactions going both ways, and the conjugate and base, or the conjugates and the acid base would just switch places. Conjugates are always on the product side, exactly, always. Yeah, so it's not like there's a component of this thing that is the acid and then another one that is the base, right? When we talk about these guys, what we're talking about is just pairs, right? And how they're able to operate within a reaction. Does that make sense? So it's not about labeling this guy an acid and that guy a conjugate base or vice versa, right? It's about knowing that acids and bases always come with a conjugate pair, right? Does that kind of help a little bit? I think this is one of the most confusing things about acids and bases, so that's why I wanted to make sure that we went over it. There is a bunch of good videos and resources in the lab for this week, but just in case y'all didn't finish the lab until after the exam, I wanted to make sure that you guys have seen this. So, coolsies. Can we do one practice problem so you guys can test yourselves on these? Yeah?
Can I ask a kind of unrelated question?
Sup?
Are we gonna have an exam in lab or like some kind of final? No.
Not
Okay,
in my
so
class,
okay.
any. You're not in my lab, so I can't.
So probably not though.
I would be amazed if somebody did that to you.
Sorry, Alex.
Sorry. Alex, I would never do that. What do I want to spend another 20 friggin' hours writing an exam? Like, I didn't spend enough
Like I didn't. One credit class. So I was
like I didn't spend enough time this semester writing every single lab from scratch. No, Alex, no exam in lab. Mommy doesn't want to deal with that anymore. Yeah, no, we're not doing it. We're not doing it. Okay, so let's do one more example just so we can test this out. Bing bong boom. Let's do how about I know. I'm sorry, Alex. Trust me, I'm as disappointed as you are. I want to light stuff on fire. And I want you guys to be able to light stuff on fire. I'm pretty sure that watching you guys do stuff with fire takes like years off of my life, but it's still so fun. I know, magnesium's so fun. We're basically playing with fireworks. It's dope.
Oh
Yeah.
my god, in the Bunsen burners, people freaked out.
Oh my gosh.
Like,
but honestly, I prefer the reaction of terror to like complete like indifference, because there are some students that are just like, whatever, fire, and be dead.
Dude, there was a point where I was literally like, they're letting us do this? The whole building like catches on fire right now.
Honestly, you guys, you have to understand how lucky we are to be able to do some of this stuff. The more time goes on, the more litigious our society becomes, the more, I promise you, those kinds of things will not be allowed. Like, even though it's an integral part of chemistry, like we used to be able to play with way more crazy chemicals in class, and now they're like, nah, it's too dangerous, which I get, you know, like, but also...
how dangerous can boiling rocks get?
Boiling rocks?
Yeah.
You mean like
Those get crazy because I got in trouble because I added way too many to them.
Oh no, that's more of a like I don't think it's a danger issue so much as it is like a wasty issue.
But I did melt the rubber of that clip that goes on the Bunsen burner thing. My professor's like, "What's that smell?" It was like
melted.
too low. Like it's like the clip that would hold.
The clip that holds a thermometer.
Yeah. Just don't. You know what?
So I'm gonna guess that was probably you had the Bunsen burner up a little too high. You were just a little too aggressive with the heating.
It was coming out. It was that way.
Yeah. So I yeah. So sometimes people get really excited with the fire and they're like, "Woo, look at me!" And I get that, you know, because like it's fun. But yeah, I'm always like, turn that down just a smidge, like a lot, like a whole bunch. Turn it down. So, my dad said his chem class in the 70s, teachers separated hydrogen and oxygen in front of the class. Yeah, totally. Yeah, we used to be able to explode stuff on a regular basis. Yeah. I mean, we still do more dangerous stuff at Mesa than a lot of the other colleges in the district. Like, I've worked at just about every college in San Diego, and we do much more fun experiments. So, anywho, all right, let's finish this example. So, who's the acid? Oh my gosh, I can't spell today, you guys.
So I have a question.
Yep.
Because I was gonna say HClO2 because HCl is in my strong acids.
Yep.
But it's linked up with O2, and that's still okay?
Oh, this isn't a strong acid.
Oh, but it's just an acid.
It is an acid, right?
Okay.
Yeah. So this guy is your acid. Anytime. So this is the only confusing part, right? When you're reacting with water, water does have a hydrogen out front, right? But remember, water can act like an acid or a base, right? If you see an H out front of anybody else, you know that guy's an acid. Does that make sense?
You're an acid.
Is everybody comfortable with that? It makes it a little bit easier when you see that the name is chlorous acid, right? Then you know it's the acid. But this guy is definitely acting as our acid, right? Which means this guy must be our
Base.
base. Cool, cool? Meow. What about these guys?
I think that the H3O is the acid.
Mm-hmm. Conjugate.
Conjugate.
And I saw Alex put that this is the conjugate base. Which I love. So not too hard, right guys? It's a little bit confusing at first, but once you understand that an acid-base reaction always has an acid and a base on the reactant side, and a conjugate acid and a conjugate base on the product side, right? Then all you need to do is figure out who's who, right? Wordy and complicated, yes. Oh, you mean like when I give you names? Like instead of chemical formulas? No. So literally the way that you could see an exam question with this would be label each one of these guys as being either the acid, the base, the conjugate acid, or the conjugate base. And just, again, I know that I've said this before, but since I'm your lab, I'm not all of your lab instructor, but I am the one that's writing all of the lab content. A lot of the questions in the labs are going to be similar to the kinds of questions that I would ask on an exam, so the sooner you do it, the better. Products are all conjugates, reactants are all not. Yep. Anytime there's an H out front is always an acid. Yes, except, and this is the big exception, this guy, right? Because water can act like an acid or a base, right? Even though there's an H out front, it can be both, right? So who it is in a given reaction would be determined by if this guy was an acid or a base. Does that make sense? Madison? Cool.
I have another stupid question.
That's not stupid. What's up?
Is it ever possible to have an acid plus an acid?
They won't react.
Cool.
Mm-hmm. Yeah, so this is kind of like the redox reactions in that the way that they react, they always partner, right? So you're never going to have an acid and an acid or a base and a base reacting. I say never. There are always exceptions to everything, okay? But you guys will never see that, right? That's like a really complicated form of chemistry where you're talking about the relative acidity or basicity, which is way more complicated than we're going to get in this class, okay? So, beep, boop, beep, boop. Questions about that, guys?
I was actually just wondering, like how, sorry, What I'm thinking in my head is not coming out of my
No
mouth.
worries. Take your time.
So, how you can tell which one's acid and base on the reactant is the same on the product side?
Yeah, so, sorry, I always use the word basically, and this is the one chapter that it always fucks up everything. So, but it really has to do with the relationship of these guys relative to each other, right? So, the most basic definition of an acid or a base is something that can donate a proton is an acid, something that can accept a proton is a base, right? So again, I think when you see a negative sign on something, that's a pretty good indication that that thing can act like a base. Does that make sense, Shion?
Yes.
Right? And you see this positive sign on here is a pretty good indication that it can act like an acid, right?
Yes. That's true when you point it out.
If there aren't...
Well, professor, on an exam you're giving as the charges, so like on a project you're giving as the charges. So
But they don't always have charges, right? In the previous example, I think we saw that the conjugate acid didn't have a plus side on it, right? So it's not that they have to have those signs, right? But it makes it a little bit easier to see when they do, right? Does that make sense? If there aren't... Yeah, so basically, you're just looking at which one of them is able to accept a proton and which one of them is able to donate, right? So honestly, that's the question that I keep in my mind when I'm trying to figure out which one of these guys is which. Conjugates are always on the product side. Non-conjugates are always on the reactant side. And whether or not these guys are an acid or a base just depends on whether or not they can donate a proton or accept a proton, right? But they don't have to have charges. The charges sometimes can be helpful, right? But I wouldn't count on that. Does that make sense? Any other questions about these guys? We're okay? Okay, so